So first, let me welcome all the participants to the thematic program on stochastic modeling with a focus on pricing and revenue management. My name is Victor Araman. I'm a professor of decision science at the Huseyin School of Business at AUB. And it gives me the greatest pleasure, really, to actually introduce our speaker today, so Huseyin Topaloglu. Before actually I almost read, even though I kind of know many of these bio, I just want to remind you that this is a first session in that second theme. The theme will run on 3 sessions. The details are on the website, and it's going to be followed by a seminar by Professor Gustavo Vulcano on the same topic of choice modeling. Back to Huseyin, again, the anecdote is, I connected with Huseyin first, and I said, let me try. Maybe he can, he can actually suggest someone if he can. And then Huseyin was extremely excited about that opportunity. He's actually, jumped on that and, contributed in thinking about the audience, how to design it and think about it. So I'm really thankful and so happy and delighted to have him with us. Huseyin, basically the professor in the School of Operations Research and Information Engineering at Cornell Tech. He got his BS in industrial engineering from not far away from Beirut in Bogazici University of Turkey, and his PhD in OR and financial engineering from Princeton. He has been a faculty member at the School of Operations Research and Information Engineering since 2002. He's currently serving as program director for the Master of Engineering program in OR, Information Engineering at Cornell Tech. So if you want to, if you're a student and you're applying there, you better impress him. Professor Topaloglu works on large-scale stochastic optimization problems that arise in areas such as revenue management, inventory control, transportation, logistics, and supply chain. He's the department editor for many top journals like Revenue Management, Department Editor for Revenue Management, Department of Product and Operations Management Journal. He serves as AE for many journals, Management Science, Mathematical Programming, Naval Research Logistics, OR, Transportation Science, IE Transactions, and surveys in OR and Management Science. So without delaying you more, Huseyin, the floor is yours, and thanks again for contributing to this program.
Thank you for your kind introduction, Victor. Victor, I'm really happy to hear, and I'm really thankful that a lot of people made it. I appreciate the time that they're putting into this. This is very nice. Thank you. And this is also really all the more important during these times because we don't get to see each other all that much. So it's a very nice opportunity again. Thanks for putting this together. So let me share my screen.
So sorry, Huseyin, to interrupt. Would you like to have it more like a casual in the sense that if people have questions, they can jump in or write on the chat and you manage that? Or do you want to wait for the end as you wish? What's
so it would be great if people jump in. And if that's not a great time for me to take a question, I'm happy to tell people, let's delay 2 more minutes or something like that. But if you have a question, please do jump in. It's difficult for me to look at the chat on a regular basis. So please, let's not use the chat. Just jump in, go for it, just like in a classroom lecture environment, live lecture environment. And, if it's not a great time for me to take a question at that point, I can ask people to delay the question for a minute or so. We can go like that.
If you can every now and then just ask them if they have a question, also that kind of maybe encourage them based on previous experience to ask. Thank you.
Please do jump in though if you got a question. Okay, so let's get started. So today we're going to do an introduction to choice modeling. We're going to talk about what we mean by choice modeling when we think about revenue management applications. And after that, we're going to formulate and solve assortment optimization problems in 2 well-known choice models. And those two well-known choice models are going to be the multinomial logit model and the nested logit model. So we're going to look at assortment optimization problems under the multinomial logit and nested logit models. So here's an outline of what we're going to do today. First, we're going to talk about what we mean by choice modeling when we think about revenue management problems. In particular, we're going to look at the customers as random utility maximizers. So in this random utility maximization principle, when a customer comes into the system, she's going to look at what options are available, and she's going to associate random utilities with those options, and she's going to pursue the option that provides the largest utility. So that's going to be the random utility maximization framework when we model the choice behavior of the customers. And by building on this random utility maximization framework, we're going to be able to come up with a whole general class of choice models, and we're going to call those choice models as the generalized extreme value choice models. And it turns out that the multinomial logit and the nested logit model are going to be two specific instances of these generalized extreme value models. So again, the first thing we're going to do is, what do we mean by choice modeling? How we can use the random utility maximization framework to capture the choice process of the customers. And after that, we're going to talk about assortment optimization problems under the multinomial logit model. In particular, we're going to look at constraint assortment optimization problems under the multinomial logit model. And the last thing we're going to look at is going to be assortment optimization problems under the nested logit model. And especially when we talk about the last two bullet points over here is the multinomial logit model assortment optimization and nested logit model assortment optimization, I would like to show you two, if you will, tricks of the trade. And what I mean by that is, for multinomial logit model, I'm going to show you how pretty standard fractional programming ideas that people have been looking at for 40, 50 years have actually been really, really useful when dealing with this assortment optimization problem under the multinomial logit model. So that's going to be the trick of the trade, if you like. So we can use fractional programming tricks to solve assortment problems under the multinomial logit model. And when we talk about the nested logit model, the assortment optimization problem you're going to see has an unwelcome and extra source of nonlinearity in nested logit model. And I'm going to show you one trick that allows us to get rid of that source of nonlinearity. So I'm going to call that the linearization trick. And we're going to see how that linearization trick allows us to solve these nested logit assortment optimization problem really, really attractively. And that linearization trick, as far as I know, appears anytime that you want to attack the assortment optimization problem under the nested logit model. Okay, so this is our agenda. So let's start by talking about what we mean by choice modeling from revenue management applications and how we can use the random utility maximization framework to capture the choice process of the customers. Okay, so what do we mean by choice modeling? So let's say we have access to a universal products. I'm going to use capital N to denote the set of products that I have access to. And whenever I need to index my products, I'm going to use the integers from 1 to little n. And what I want to do is the following. Given that we offer the subset S, given that we offer the assortment S of products, I want to come up with a model that tells me what is the probability that a customer is going to purchase each product I within the offered assortment. So that's what I mean by choice modeling. I have universal products. Given that I offer a subset and assortment of these products, I want to come up with a choice model that tells me what's the probability that each customer is going to go for each one of these products that I offer. So let me try to give you an example. Let's imagine that we're selling a laundry detergent. And the products we can offer to our customers, a Tide laundry detergent or an Arm & Hammer laundry detergent. So then I want my choice model to say something like this. If you offer the Tide laundry detergent, but not the Arm & Hammer laundry detergent, then 50% of your customers is going to go for Tide, and 50% of customers is going to go for the no purchase option. They're going to leave without it. On the other hand, if you offer Arm & Hammer, but not Tide, then 70% of your customers is going to go for Arm & Hammer. 30% of your customers is going to go for no purchase. On the other hand, if you offer both Tide and Arm & Hammer in your store, then let's say 40% of your customers is going to go for Tide, 50% is going to go for Arm & Hammer, 10% is going to go for no purchase option. So this is what I mean by choice model, right? If I offer an assortment of the products that I have access to, what's the probability that my customer is going to go for each one of the options that I offer them? One obvious way to do this is I'm going to denote phi of S. I'm going to let phi of S be the choice probability for product I when I offer the assortment S. So this is the choice probability of product I when I offer the assortment S. So one way of modeling the choice behavior of the customer is we estimate and list this choice probability for every possible assortment and for every product that we can offer to our customers, right? And that would be probably something super clumsy. You want to estimate a single number for every assortment and for every product that you can offer to your customers. That is going to be, first of all, a lot of numbers to estimate. And maybe also there's going to be some inconsistencies between those estimates, and checking for these inconsistencies is going to be hard. So we're going to do something a little bit more interesting, a little bit more intelligent than that. So we're going to refer to this random utility maximization framework. So what happens in the random utility maximization framework is that when a customer comes in, she's going to associate random utilities with each one of the products that are offered. And she's also going to offer a random utility with the no purchase option. And she's going to look at, what these utilities are, and she's going to go for the product that provides she's going to go for the option, let me say, that provides the largest utility. The option could be one of the offered products or the no purchase option. Okay, so that is what we mean by the random utility maximization principle. So let's try to make this principle a little bit more concrete. So when a customer comes into the system, she's going to associate a random utility with each product I, and I'm going to denote the random utility of product I by UI. And this random utility of product I is going to have two components, a deterministic component UI and a random component epsilon I. Okay. And sometimes people call this deterministic component as the systematic component and the random component as the idiosyncratic component. But the bottom line is the utility of each product I is going to have a deterministic component plus a random shock on top of that. Similarly, the customer is going to associate a random utility with no purchase option that has got a deterministic component in it and a random component in it. U0 is going to be the utility of the no purchase option. So then, what did we say under the random utility maximization principle? When a customer comes into the system, she's going to associate utilities with each one of the available options and go for the option that provides the largest utility. So then under the random utility maximization principle, if I offer the assortment SO products, the probability that a customer goes for, the probability that the customer purchases product I is given by, if I offer the assortment SO products, the probability that the customer purchases product I is given by, the probability that utility of product I is greater than the probability of is greater than the utility of all available options, and utility of all available options being the utility of each product J in the offered assortment, and utility of the option 0, utility of the no purchase option. So this is a pretty generic way of describing the choice process of the customers. Customers come in and associate random utilities with the products and the no purchase option and goes for the available alternative that gives you the largest utility. So give me any distribution for the utilities. I can conceptually do this probability computation that will give me the choice probability of product I, any assortment. So this is a nice conceptual framework, but for general distribution of the utilities, this probability computation may not be a tractable computation to do. You may have to compute, big integrals, maybe you do Monte Carlo simulation or whatnot. For general distribution of the utilities, this probability computation may not be easy. So now what we're going to do is we're going to look at a specific distribution of these random shocks. So we're going to basically look at the case where the cumulative distribution function of these noise terms, epsilon 0, epsilon 1, dot, 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 epsilon n, these are the noise terms for the utilities of each one of the products and the no purchase option. So we're going to look at the case where the cumulative distribution function for the random utilities has this double exponential form. And I say this is double exponential because we have an exponential over here and we have an exponential over inside, and G over here is a general function. So this is going to be the form of the cumulative distribution function for the utilities of the different options, or for the random portions of the utilities of the different options. So this is the CDF. So this is the probability that the utility of the no purchase option is less than or equal to x0, utility of the first option is less than or equal to x1, that utility of the last option is less than or equal to xn. So this is supposed to be a CDF. So for general G, for a general function, there is no reason that this function should be for a general G, there is no reason that this function should be a legit cumulative distribution function. But you can come up with a set of sufficient conditions that ensures that this function that we wrote on the top is indeed a cumulative distribution function. And those are these are in green, the conditions that ensure that the function that we wrote on the top is indeed a valid cumulative distribution function. We can read through what these conditions are. First, we need to make sure that this G function is non-negative. Second, we need to make sure that if I have a constant lambda multiplying all of the components of the G function, I can pull that lambda out of that G function without disturbing the value of the G function. So that is positively homogeneous with degree 1. That's what that property says. This property says if I increase one of the components in the arguments of the G function, G is going to blow out to infinity. And lastly, this property says if I look at the cross derivatives of G along k directions, this cross derivative is going to be positive if k is odd, and this cross derivative is negative is k0. It turns out that if G satisfies all of these three conditions, then it's guaranteed that this function that we wrote here is going to be a valid cumulative distribution function. That is nice, but I'm going to be able to tell you something even nicer, and that is the following. That is what's written at the very bottom of the slide. So I'm going to be able to tell you something even nicer, and that's the following. So let's look at the case where the utility of each product I and the utility of the no purchase option can be written as a deterministic component mu plus a random shock. And let's assume that the customers are utility maximizers. And let's also assume that the cumulative distribution function for the noise terms has this double exponential form that we have on the top of the slide. then I can give you a closed form expression for the choice probability of each product out of the full assortment of products. The probability that a customer goes for product I, when I offer the full assortment of products, is given by e to the deterministic portion of the utilities times the first derivative of this g function, they call that the generating function, the first derivative of the g function, evaluated at these e to the mu i's, divided by the g function, evaluated those e to the mu i's. So when the noise terms has this double exponential cumulative distribution function, it turns out that that probability computation that tries to figure out the probability that the utility of product I is greater than the utility of all the available other options, that thing has a very nice closed form expression, and it is this expression. Okay, so now this opens a whole big sort of window of opportunity for us to come up with all kinds of different choice models. Come up with any kind of G, any kind of generating function, come up with any kind of G that satisfies these properties. That gives you a distribution, cumulative distribution function for the random noise terms. And under that cumulative distribution function for the random noise terms, I can give you a closed form expression for the choice probability of every product. So this gives you, again, many, many different kinds of a broad class of choice models that you can work with. And those classes of choice models is called the generalized extreme value models. So corresponding different choice of G, we're going to end up with a different generalized extreme value model. So today, we're going to look at two very well-known generalized extreme value models, and those models correspond to two different choices of G over here. And the first one is going to be the multinomial logit model. If I choose my G function just as the sum of these x's, then it turns out that this expression that we have on the previous slide, e to the mu I, the partial derivative of gi divided by g. If I choose my G function as the sum of the x's, e to the mu I, the partial derivative of g with respect to any of the components is going to be 1 divided by the G function evaluated at the e to the mu's. It's going to take this form. So if I choose the G's as the sum of all of its components, then the choice model that I end up with is going to have this form of the choice probability, and that choice model is called the multinomial logit model. So the well-known multinomial logit model that we've been all using with is a special generalized extreme value model for a specific choice of the generating G function, where this G function is a simple sum. On the other hand, here's another choice of the G function. If I choose G function in this way, namely x0 plus x's raised to 1 over gamma, and the whole sum added up and raised to another gamma, and gamma is a number between 0 and 1. Over here, this almost looks like a distance function. For example, if you choose gamma equals to 0.5, I'm squaring all the x's and taking their square root. So if G has this distance kind of a function, then if I again look at the previous formula and apply it, the choice probability of product I under the full assortment is going to have this form, and this choice model is called the nested logit choice model. Okay? And again, different choice of G is going to give us different choice models. Today, we're going to concentrate on these two specific forms of G that give us the multinomial logit model and the nested logit model. And so far, I have been talking about the choice probability of product I if I offer the full assortment. And we're not always going to offer the full set of the products. So if I'm interested in the choice probability of product I, when I offer a subset S of products, what I can do is I can compute the choice probability of product I out of the full assortment after setting the deterministic portion of the utility of each product J that is not offered to minus infinity. If the deterministic portion of each product, utility of each product J that is not offered is minus infinity, then those are products that will never be chosen by the customer. Their utility is always going to be minus infinity. So then if I want to compute the choice probability of a product out of a not full assortment, out of some assortment S, I can use the same formulas. After setting the deterministic portion of the utility of the unoffered products minus infinity, and use the same kinds of formulas. So these formulas are generally enough to give me the choice probability out of not full assortment, out of smaller assortments. Okay, so this is again what the random utility maximization principle is, and then we can specialize the random utility maximization principle where the distribution of the utilities has this double exponential form. We get a closed form expression for the choice probabilities. And by using specific choice of this generating function G, we obtain the multinomial logit model and the nested logit models. And there are many, many other different choices of G that give us different kinds of other choice models. There's another choice of G that gives me the cross-nested logit model. There's another choice of G that gives me the paired combinatorial logit model. So you can come up with all kinds of other different choice models by using different types of G. But today we're going to look at the multinomial logit model and the nested logit model. Okay, So this is a good place for me to take a breath. If anybody has questions, comments, let's hear.
Sorry, can I ask a question? Thank you. So I was thinking conceptually about these noise terms. So from the customer perspective, is utility deterministic, or do they experience as well this randomness when choosing something?
Yeah, so let's not think, so from a customer perspective, their utilities, it's a model, so you don't know. It's neither, right? You don't know, it's a model. So the way I would look at this model is the following. The customers may know what their utilities are, but as a seller, I don't observe utilities of the customers. So you may come in, you may have certain set of utilities. I may come in, I may have another different set of utilities. As a seller, which is our goal, as a seller, I'm going to model the utilities of the customers as deterministic. I'm going to model the utilities of the customers as random quantities, because you may be the purchaser, I may be the purchaser, he may be the purchaser, she may be the purchaser. I don't know which purchaser I'm going to face. So even if the customer's utilities are deterministic, they know what it is. Since I don't know which customer I'm going to hit by, I think it's reasonable to model the utilities of the customers as random. Reasonable?
Yeah. Okay. Thank you.
Great. Of course. Okay.
Sorry, one question. So I understand this family of double exponential distributions is a large space. But why is it reasonable? Why that CDF makes sense? Like, are there other distributions that we expect a function, a product of this family, like apart from MNL and stuff?
Yeah, I don't have a, so there is, I don't, as far as I know, there is no structural reason why we should assume that this should be the behavior of the customers. I think the most basic reason that we go for generalized extreme value models is we get this beautiful closed form expression. That is one. Second is when people work with empirical data, these kinds of distributions has been reasonably flexible enough that there is broad enough generality, broad enough class of generalized extreme value models that one of them has been working reasonably well. And the third is if you can mix enough number of multinomial logit models, which is something that I'm going to get to at the very end, if you mix enough number of multinomial logit models, it can capture any kind of utility distribution. So there is these kinds of denseness results as well. So these are the reasons that people go for these go for these generalized extreme value models. But as far as I know, there is no real structural reason that people should be choosing according to this kind of utility distribution. But it gives us nice closed form expressions. In practice, these things tend to work well. And there's a denseness result that says if you mix enough multinomial logit models, you can capture any utility distribution that you like. Okay.
Yeah, thank you.
Okay, so let's move on. Let's think about formulating constraint assortment optimization problems under the multinomial logit models, and we're going to use fractional programming tricks in this domain. We're going to see that these fractional programming tricks actually go a long, long way when we're solving assortment optimization problems under the multinomial logit model. Okay, so let's first think about what we mean by assortment optimization. So here's what I mean by an assortment optimization problem. So we have access to a whole bunch of products. Each one of these white boxes is a product that we can offer to our customers, and there is this no purchase option here. We're going to offer an assortment. We're going to offer a certain subset of these products. And a customer is going to come in. She's going to make a choice within these offered products according to the multinomial logit model here. And our goal is to figure out which of these products to offer to our customers so that we maximize the expected revenue from a customer's visit. So that's what we mean by an assortment optimization problem. Okay. So let's try to formulate our assortment optimization problem under the multinomial logit model. We have n products. We're going to index the products by 1 to n. And we're going to encode our assortment decisions by these n-dimensional binaries, x1 to xn. And the jth component of this binary vector is going to take value 1 if and only if we product j. Okay, if only if we offer product j. So we're encoding our assortment decisions by these n-dimensional binaries. And the jth component of this binary vector is going to take value 1 if and only if we offer product j. So in the multinomial logit model, we're going to use Vj to denote the preference weight of product j. Vj is going to characterize how attractive product j is to a customer. The larger Vj is, the more likely that a customer is going to go for product j. So then under the multinomial logit model, if our product offering decisions is given by this vector x, the probability that the customer purchases product j, the probability that the customer chooses product j is given by the preference weight of product j divided by the preference weight of all available options. And the preference weight of all available options are look at each product that I can offer and add up the preference weights of the offered products plus the preference weight of the no purchase option. Here I normalize the preference weight of the no purchase option to 1. So this is the choice probability of product J under the multinomial logit model, given that our assortment offering decisions is given by this binary vector X. And if you want to map this choice model to the multinomial logit model that we just discussed, remember over there, the choice probability of a product was e to the mu I divided by the sum of the e to the mu's for all the offered products. So here we're doing nothing more than using Vj, this preference weight, to denote the e to the deterministic portion of the utility of the product. Okay, so Vj maps it to e to the mu j when we were talking about the generalized extreme models. So this is the form of the choice probability under the multinomial logit model. So then we can write our assortment optimization problem. We're going to let Rj be the revenue of product J. So this is how much money we make if we sell 1 unit of product J. And on top of the assortment that we can offer to our customers, we're going to put a constraint. And these constraints are going to be characterized by a constraint matrix with entries Aij's. And I would like this constraint matrix to be a totally modular constraint matrix. And by a totally modular constraint matrix, I mean it's a matrix where I'm solving like a linear program AX less than, where I'm solving a linear program with constraints AX less than or equal to B. I want that linear program to have integer extreme points when B is an integer. Okay, so we're going to look at assortment optimization problems under the multinomial logit model with a totally modular constraint structure. So let's then write our assortment optimization problem. I'm trying to figure out a vector, an assortment S of an assortment X of products that I'm trying to offer. If my assortment offer decisions is given by the vector X, this is the probability that a customer chooses product J. If she chooses product J, this is the revenue that I obtain at overall product. So that is the expected revenue that I obtain by making the assortment offer decisions X. And here are the constraints that limit my assortment offering decisions. Take the assortment offering decisions for product J, multiply by the corresponding entry for product J in the ith constraint at overall products. That is going to be less than or equal to some generic right-hand side. And I have L of these constraints. And I'm going to give you specific instances of what these constraints may look like in practical applications. So this is my assortment optimization problem that I would like to solve. Let me emphasize a few aspects here. First one is obviously we have binary decision variables. Second, these choice probabilities are given by a fraction. So the objective function is nonlinear. And I have a whole bunch of constraints on my decision variables. So this is a binary nonlinear constraint optimization problem, if you like. Okay, so this is the problem that I would like to solve. So we got this nonlinear binary constraint optimization problem. It looks pretty gnarly, but the main result that we're going to see in this portion of the lecture is that it turns out we can take this binary nonlinear constraint assortment optimization problem and immediately formulate as a pure linear program. And here's that equivalent linear program. So we're going to show that these two problems are perfectly 100% equivalent to each other. And let me try to give you a feel for what this linear program looks like. Let me try to give you a feel, some intuition for what this linear program does. In this linear program, interpret the decision variable Yj as the probability that a customer purchases product J, and interpret Y0 as the probability that the customer goes for the no purchase option. Well, this is the probability that a customer goes for product J, and if she goes for product J, this is the revenue that we obtain. In the objective function, I'm trying to maximize the expected revenue. This constraint says a customer is either going to go for some product and it's going to go for the no purchase option. So the total probability that a customer goes for a product or the no purchase option has to add up to 1. This constraint ensures that the choices of the customers, the choice probabilities for the products are aligned with the multinomial logit model. So this constraint aligns the choice probabilities with the multinomial logit model. And this constraint ensures that the choice probabilities are going to come from an assortment that is obeying the constraints that I'm interested in. So this is the form of the linear program. And again, our main result that we're going to see in this portion of the lecture, we can take this binary nonlinear constraint problem and equivalent formulate as a pure linear program. So things are very nice when we're trying to solve assortment optimization problems under the multinomial logit model with a totally modular constraint structure. Okay, so that's the main result we're going to see. But before we see where this result is coming from, let me try to give you a few examples of why should I be interested in solving assortment optimization problem under totally modular constraints? In what kind of areas do I get to see totally modular constraints? Well, here's one area. let's imagine that I want to solve an assortment optimization problem where I have a cardinality constraint on the number of products that I can offer to my customers. How do I model a cardinality constraint? Well, I say xg is going to take value 1 if I offer product j to my customers. So if I can offer no more than c products to my customers, the cardinality constraint on the number of products that I can offer to my customers can be written as sum of the xj is going to be less than or equal to c. In that case, my constraint matrix is going to have one row, and every entry in that row is going to be a 1. That is one row of all ones. That is a totally modular constraint matrix. So then maximizing the expected revenue under MNL with a cardinality constraint is maximizing the expected revenue under the multinomial logit model. MNL refers to multinomial logit model. Maximizing the expected revenue under the multinomial logit model subject to a one line of ones, which is a totally modular constraint matrix. So I can capture cardinality constraints by my totally modular constraint structure. So that is one application where totally modular constraints come into play. Cardinality constraints on the offered assortment. I can do a little bit more complicated, a little bit more interesting cardinality constraints. So for example, I can say, out of all of your products, offer no more than C1, okay? Out of your moderately expensive products, offer no more than C2, and out of your most expensive products, offer no more than C3. So I can have this kind of nested cardinality constraints. So then if I look at the constraint structure for this kind of nested cardinality constraints, well, in the first constraint, I have ones all over. There's that. In the second constraint, I have ones for only the moderately expensive products. There is that. And in the third constraint, I have all ones for the most expensive products. There is that. So this is the structure of the constraint matrix when I have this kind of nested cardinality constraints. In this constraint matrix, each row includes a consecutive ones. There is consecutive ones, there is consecutive ones, there is consecutive ones. These matrices where each row includes consecutive ones, they are known as interval matrices, and they're also known to be totally modular. So again, if you're interested in maximizing expected revenue subject to these kinds of nested cardinality constraints, that also gives you a totally modular constraint structure. So I can maximize the expected revenue under the multinomial logit model with these nested cardinality constraints by using my linear program. Okay. So let's move away from cardinality constraints. Let's do something a little bit more interesting. Let's think about location-specific preference weights. So in many applications, brick or mortar or online, whether a customer is attracted to a product or not, or how much a customer is attracted to a product, depends on where you display the product to the customers. So for example, in a supermarket, if you offer a product at an eye level versus if you offer the product at an E level, the attractiveness of the product could be different to the customers. Or in online retail applications, if you offer a product at the top of the search results or towards the bottom of the search results, the attractiveness of the products may be different to the customers, right? So then we may have preference weights of products that are dependent on the location at which we show the products to the customers. So let's try to write down an assortment optimization problem where the preference weights depend on the locations of the customers. It turns out that the totally modular constraints are going to appear in that setting as well. So to formulate the problem, let's extend our assortment offering decisions. So to capture our assortment offering decisions, I'm going to use xjls, and xjl takes value 1 if we offer product J at location L, otherwise xjl takes value 0. So I'm not only thinking about what products to offer, I'm also thinking about what location do I offer them. And again, xjl takes value 1 if I offer product J at location L. And let's say VJL is the preference weight of product J when we offer this product at location L. So then, if my product offering decisions is given by this vector of binaries xjls, the probability that customer picks up product J from location L is given by the preference weight of product J at location L divided by the preference weights of all products at different locations that I offered and the preference weight of the no purchase option over here. So those are my choice probabilities when I extend the assortment decisions by the locations and the products. So now let's write our assortment optimization problem. I'm trying to maximize the expected revenue. This constraint says every product J, if offered, can be offered. This constraint says every product J, if offered, can be offered in at most one location. This constraint says every location L can include at most one product in it. Okay, so that is the constraint structure. This constraint says you can offer each product J in at most one location. And this constraint says every location L can include at most one product in it. So then if you look at this constraint matrix, that is the constraint matrix of a transportation problem on a bipartite graph. On the left side of this bipartite graph, let's put one node for each product J. Let's put one node for each product J. On the right-hand side, we put one node for each location L. So these constraints are saying, the total flow out of each node J on the left is less than or equal to 1. The total flow out of each node J on the left is less than or equal to 1. And these constraints are saying the total flow into each node L on the right is less than or equal to 1. So again, this is the constraint matrix of the transportation problem on a bipartite graph that is known to be totally modular, so that we can capture assortment optimization problem with location-specific preference weights by using totally modular constraint matrices. So this problem can be solved as a linear program as well. So before I bore you to death, I'm going to give you one last example and wrap up the applications over there. And the last application we're going to look at is joint pricing and assortment optimization. In many applications, we do not only think about whether we offer the product or not, but we also think about at what price do we offer the product or not to our customers. And the attractions of the product, may depend on the price that we offer, the price at which we offer the product. Like, for example, if I'm buying airline tickets from New York to Istanbul, if this Turkish airline ticket is offered at $1,200, my attraction to that product is going to be something. But if it's offered at $800, my attraction to that product is going to be something else. So now let's think about modeling joint assortment optimization and pricing decisions. To capture joint assortment optimization and pricing, we're again going to augment our assortment decisions. So let's say XJL is going to take value 1 if you offer product J at price level L. So I'm assuming that there's a discrete set of different price levels at which I can offer a product. $100, $110, $120, $130, whatever. So in my assortment decisions, XJL takes value 1 if you offer product J at price level L. VJL is going to be the preference weight of product J when we offer this product at price level L. And likewise, RJL is going to be the revenue that we obtain from product J when we sell this product at price level L. When the price level L increases, presumably these revenues are going to increase. But when price level L increases, presumably these preference weights are going to decrease. The product is going to be less attractive to the customers. So then, if my, again, pricing and assortment decisions is given by this vector of XJLs, this is the probability that a customer picks up product J at price level L, the preference weight of product J at price level L, if it's offered at that price level, divided by the preference weights of all the products offered at their corresponding price levels. So then here is my expected revenue that I'm trying to maximize. This is the probability that a customer picks up product J at price level L. If she picks up product J at price level L, that's the revenue that I obtain at overall products at different price levels that I can offer. This is the expected revenue that I'm trying to maximize. And this constraint says each product J, if offered, can be offered at most 1 price level. All of the XJLs can be 0. In that case, you don't offer the product at all. But if you're going to offer the product, you can offer the product at most 1 price level. Okay, so this is my assortment optimization problem when I'm trying to choose both the assortment of products offered and their corresponding price levels. So now let's look at this constraint matrix. Well, in this constraint matrix, for every product J, I have 1 constraint. So for product 1, I have 1 constraint. For product 2, I have 1 constraint. ... For product N, I have 1 constraint. And for the constraint that corresponds to product J, I'm looking at the offering decisions for product J corresponding different price levels, and I'm adding them up. So this is product 1 offered at price level 1. This is product 1 offered at price level 2. Product 1 offered at price level 3. Offered at product 1. Oh, product 1 offered at price level 4. Their sum is less than or equal to 1. Likewise, product 2 offered at price level 1, 2 at level 2, 2 at level 3, 2 at level 4, and their sum is going to be less than or equal to 1. So again, this is a constraint matrix where each row includes a whole bunch of consecutive ones. As we said before, these things are known as interval matrices. They are totally modular. So I can model assortment and price optimization problems as an assortment optimization problem with a totally modular constraint matrix. So now I can, by using our result, we can solve these kinds of problems as linear programs as well. Okay, so anybody has anything to say about the applications before we move on to the proof of equivalence between these 2 problems that we have here?
Sorry, one question. What if the price space is continuous? Can we still use that method?
If the price space is continuous, There are different results. I want to stay discrete in this lecture because we're doing assortment optimization. There are other results I can point them to at the end of the lecture. Yes, there are a whole bunch of results in that domain.
Cool, thank you.
But for my money, if you got discrete problems, if you got continuous problem spaces, discretize the hell out of it, you can still use these results. Right? You can discretize with increments of pennies, we're good to go. Okay? But there are specialized results for continuous optimization. I'm not going to get into those. Good. So now let's get our first major result for this lecture. We want to show that this binary nonlinear constraint assortment optimization problem is fully equivalent to the linear program that we have on the lower right-hand side. And we're going to use these fractional programming tricks, and let's see how these things are going to play out. Okay. Here is the problem that I would like to solve. Maximize the expected revenue subject to a whole bunch of totally modular constraints. The first thing we're going to do is we're going to write this expected revenue expression in a more explicit form. This is the choice probability of product J, given that our assortment decisions is given by the vector X. Here that is the choice probability of product J, given that our assortment decisions is given by the vector X, that's the choice probability. Times the revenue of product J, added overall products. This is the expected revenue written in explicit form. So I didn't do anything, I just wrote down the expected revenue under multinomial logit model in more explicit form, subject to my totally modular constraints. So this is the problem that I would like to solve. I would like to maximize this fraction subject to totally modular constraints with binary decision variables. And let's let Z star be the optimal objective value of my assortment optimization problem. That's the problem that I would like to solve. Okay, good. So now here's our first observation. I want to solve this problem. Its optimal objective value is Z star. So it turns out then I want to solve this problem. Its optimal objective value is Z star. I want to solve this problem. Its optimal objective value is Z star. So then what I can say is the following. Well, for any assortment offering decisions X that are feasible, the optimal objective value of my problem Z star has to be greater than or equal to the expected value computed at those assortment decisions. And at the optimal assortment decisions, this inequality has to be tight. Let's say it again. The optimal objective value of this problem is Z star. That means that for any assortment decisions X that are feasible according to my constraints, the optimal objective value of my problem has to be greater or equal to the expected revenue at those assortment decisions. And at the optimal assortment decisions X star, this inequality has to be tight. So that is the argument that I want to pass on in this last panel. Okay. Here is that argument that we had in this last panel. Good. So now let's write this inequality in a slightly different fashion, in an equivalent but slightly different fashion. Take the denominator, throw it to the left-hand side. So in that case, what are we going to get? Z star plus sum over J, Z star Vjxj. Take sum over J, Z star Vjxj, throw it to the right-hand side. So now what we have here is sum over J, Rj Vjxj, sum over J, Rj Vjxj, minus Z star Vjrxj, add over J, minus Z star Vjxj, add over J. These two inequalities are perfectly equivalent to each other. All I did was take the denominator, throw it to the left-hand side. So Z star plus sum over J, Z star Vjxj. Take sum over J, Z star Vjxj, then throw it to the right-hand side. These two inequalities are 100% equal to each other, equivalent to each other. So what that means is that for any assortment decision X that is feasible according to my constraints, the optimal objective value of my assortment has to be as large as this quantity evaluated at the assortment decisions. And at the optimal assortment decisions, this inequality has to be tight. What that means is that if I maximize this objective function, overall feasible assortment decisions, this should recover me the optimal assortment. And furthermore, if I maximize this objective function, overall feasible assortment decisions, I should be making this inequality tight. So the optimal objective value of this problem has to be exactly equal to Z star. Okay. So by using this fractional programming trick, I reduce the problem where I'm trying to maximize a fractional objective function to the problem where I maximize a linear objective function, but I don't know the value of Z star. Okay. But I can solve this problem to recover the optimal assortment decisions as well. It's just that I don't happen to know what Z star is, but let's stick with that. Good. So now let's again copy that last panel on a fresh page. That is my fresh panel. So then this top expression tells me that I can view the value of Z star, the optimal expected revenue in my assortment optimization problem, as satisfying a fixed point equation. What do I mean by that fixed point equation? As a function of Z, let me denote the optimal objective value of this problem as f of Z. Here it is. As a function of Z, let me denote the optimal objective value of this problem as f of Z. Okay. So then what is this number over here? What is this number over here? That is exactly equal to f of Z star. So then this argument tells me that if I denote the optimal objective value of this maximization problem as f of Z, then Z star has to satisfy this fixed point equation. F of Z star is exactly equal to Z star. So then the question of computing the optimal expected revenue in my assortment optimization problem has reduced to computing the fixed point of a function f. And when I need to compute the fixed point, when I need to compute this function f, I need to solve a maximization problem that looks like this. But the problem of computing the optimal expected revenue reduced to the problem of computing the fixed point of this function f. Computing the fixed point that satisfies f of Z equals Z, computing the fixed point. Okay, so then all that I need to do now is compute the fixed point of this function. Find a point Z star that satisfies f of Z star is exactly equal to Z star. Good. So the last thing we're going to do is we're going to take the question of computing the fixed point of this function and roll it into our optimization problem. And here's how we're going to be able to roll the computing the fixed point of a function into this optimization problem. So I want to now compute the fixed point of Z while also X's are also decision variables. And I don't like the problem in this form because Z's and X's are interacting with themselves in a nonlinear fashion. The first thing I'm going to do is I want to make sure that Z's and the X's are not going to interact in a nonlinear fashion. Here's what we're going to do. Let's look at this problem. For a fixed value of Z, the objective function is linear in X. And this is also linear in X. Okay. And the constraint matrix is totally modular, which means that if I relax these binary constraints to take values between 0 and 1, if I relax them to be continuous variables between 0 and 1, I will get integrality for free because I have totally modular constraint matrix. So then I can compute f of Z by not solving a binary problem, but by solving just a linear program. So f of Z can be solved by a linear program. So instead of solving f of Z by solving this linear program, I'm going to compute f of Z by solving its dual. So let's write down the dual of f of Z. Let me associate a dual variable gamma I with this constraint. And I have these constraints that says xj's are between 0 and 1. Let me associate a dual variable mu j with those upper bound constraints. So then the dual of this problem is given by, well, we're going to minimize mu j times 1 added over all j, bi times gamma I added over all I, and these are going to be my dual constraints. So I can now solve f of Z, I can now compute f of Z by solving the dual of this problem, and here's the dual of this problem. The reason that I love this dual is the following. My decision variables are mu and gamma. Now Z doesn't interact with mu and gamma, right? They are not multiplying with each other. Over my decision variable X multiplied Z, so they were interacting in a nonlinear fashion. In the dual, mu's and gammas are not interacting with Z's. That's why I like computing f of Z by using the dual. Good. So the final thing that we would like to do, remember, we want to compute the fixed point Z star that satisfies f of Z exactly equal to Z star. It turns out that I can solve one linear program to find the value of Z that satisfies f of Z equals Z. Here's how we're going to do it. This is the linear program that computes f of Z for a fixed value of Z. Let me copy that. That's the linear program that computes f of Z for a fixed value of Z. And I want to find a value of Z that satisfies Z equals f of Z. In order to ensure that, I'm going to add one more constraint that says the objective value of this problem is exactly going to be equal to Z. And I'm going to optimize this problem now over the decision variables mu's, gammas, and Z's all together. Then you can show that this problem automatically computes the fixed point of this function. And the intuition is that this portion is computing, this minimization portion is computing f of Z for a fixed value of Z. Then I added the constraint that says the objective function has to be exactly equal to z. That gives me the f of z exactly equals to z constraint. And if you optimize this problem again over all the mu's, gammas, and z's together, you can show that this thing is going to compute a fixed value of z, fixed point of this function f. And if you take the dual of this problem, just a blind to take the dual, you obtain the linear program that I showed you at the very beginning. Okay. So then rolling back, what are the arguments? What are the ingredients of the argument? What are the ingredients of the argument? We wrote our optimization problem. We wrote our assortment optimization problem under MNL as maximizing a fraction subject to whole bunch of totally modular constraints. And then we said we did a fractional programming argument. We said, well, if you're trying to solve this problem, whose optimal objective value is z star, then at any feasible solution to this problem, z star should be greater or equal to the objective value evaluated at the feasible solution. At the feasible solution, this equality has to be tight. This inequality has to be tight. There's that. There's that. So then we wrote this inequality in a slightly different fashion. Basically, put the denominator to the left-hand side and arrange these things. And this inequality is equivalent to this inequality. So by, again, our fraction programming argument, for any feasible assortment that satisfies all of our constraints, this optimal expected revenue should be at least this much. And at the optimal assortment, this inequality has to be tight, which means that I can maximize this expression subject to the feasibility constraint to recover my optimal assortment. And at the optimal solution, this inequality has to be tight. So the optimal objective value of this problem should be exactly equal to z star. So now let's go to the next slide. So then I can solve this problem to recover my optimal assortment. So then this immediately showed us that z star, the optimal expected revenue in our problem, has to satisfy a fixed point equation. Namely, let me denote the optimal objective value of this problem as a function of z as f of z. Then z star has to satisfy a fixed point problem, f of z star exactly equal to z star. So then computing z star becomes just equivalent to computing the fixed point of this function f. So then I want to compute the fixed point function of this function f. Now I want to roll that fixed point computation into a math program. In order to roll that fixed point computation into a math program, what did we do? Well, my z and x is interacting with each other in a nonlinear fashion. I don't like that. Let me separate them out. In order to separate them out, for fixed z, this is a linear program with a totally unimodular constraint. So I can relax the binary constraints to continuous constraints. Then instead of computing f of z by solving the primal, I can compute f of z by solving its dual. The beauty of the dual is when I compute f of z by solving its dual, the beauty of the dual is the decision variables mu and gamma do not interact with z. They don't multiply each other. So then I can compute my f of z by solving this dual problem. The last thing that I need to do is write a math program that computes the fixed point of f that satisfies f of z exactly equal to f. And there is that math program that computes a fixed point of f. This portion computes the f of z, and I put this additional constraint that says the objective function has to be exactly equal to z. This ensures that this math program both computes f of z and also finds a value of z that satisfies f of z exactly equals to z. And taking dual, we obtain this linear program that I showed you at the very beginning of this portion of the lecture. Okay, this is a good point to stop. Any questions?
Sorry, we only have one fixed point, right? We cannot have multiple ones.
Yes, you can have only one. You have only one fixed point, and if you want to see that really quickly, so I'm trying to compute f of z exactly equals z. Yeah.
Mm-hmm.
So let's put z.
Decreasing.
So this is z equals z, and f of z is decreasing in z. So f of z is looking like that. So there's going to be, this is f of z. There's going to be one fixed point. That is the optimal objective value of our problem, which makes sense. Our problem is going to have a single optimal objective value. It cannot have two of those. Good. Great. Thanks. Anybody else? Okay. So now we know one nice little cute result that shows us the assortment optimization problem under the multi-node logit model, even with totally modular constraints, can be solved as a linear program. And there are a whole bunch of applications that can be modeled using totally modular constraints. So now let's move to the assortment optimization problem under the nested logit model. Let me try to give you a high level motivation for the nested logit model. Why do we need nested logit model? Let's assume that we're a company like Home Depot. We're selling hardware supplies. And let's say we're offering this hammer in our store. And when we offer this hammer in our store, 50% of our customers goes for the hammer, and 50% doesn't like the hammer and they leave the store without purchasing anything. So if you want to capture this situation, a reasonable thing to do is associate a preference weight of 1 with the no purchase option, preference weight of 1 with the hammer. In that case, if you use the multinomial logit model, it's going to come back and say 50% of our customers goes for the hammer and 50% leaves without a purchase. Good. Let's imagine that we have another hammer that looks very much like this hammer, but maybe has a slightly different color and the handle. So now when I offer that hammer, well, it's very much like my first hammer. 50% of my customers is still going to go for that hammer and 50% are going to leave without a purchase. So then to model this situation by using my multinomial logit model, again, I associate a preference weight of 1 with my hammer, preference weight of 1 with the no purchase option. So then multinomial logit model is going to come back and say, well, 50% of your customers goes for the hammer, 50% leave without a purchase. Good. But now let's think about a scenario where I go ahead and say, I'm going to offer both of these hammers altogether. So now what is my multinomial logit model going to say? Well, the preference weight of each one of these options is 1, 1, 1. So then probability that a customer is going to go for the first hammer is going to be 1 divided by 1 no purchase and the preference weights of the 2 hammers that I offer, so 1/3. Likewise, 1 divided by 1, 1, 1, 1/3, and 1/3 for the no purchase as well. Is there a reasonable expectation of what should be happening in the market? When I offer just this hammer by itself, I could grab only 50% of the market. And I went ahead and offered another hammer that looks very much like the other hammer that I was offering. I was almost duplicating the same hammer, except that the handles have different colors. And multinomial logit model came back and told me that, well, you know, if you offer these 2 identical hammers, now you're not going to be only commanding 50% of the market. Now you're going to be commanding 66% of the market. And that is an unrealistic expectation of probably what's going to happen to the market. This new hammer that I'm offering should not really help me to extract another 16% of the market because these 2 hammers are virtually equivalent to each other. Maybe a more reasonable expectation of what should happen in the market is, if I offer 1 hammer, I'll be grabbing 50-50. But if I offer 1 more hammer, which is very similar to what I was offering before, well, you know, maybe I'm going to get a little bit more than 50. What am I getting here? Maybe I'm going to get 52% of the market. But this other hammer that I just offered, which was very similar to the hammer that I was offering before, should not get me too much more of the extra market. So this is one shortcoming of the multinomial logit model. If I keep on offering products that look very similar to each other, multinomial logit model is going to think those extra products that I keep on offering is going to keep on attracting a large fraction of the market, whereas the benefit from those extra hammers might be actually very marginal. So the nested logit model makes up for these deficiencies. So let's try to describe how the choice model of how the choice process of the customers work under this nested logit model. So we're going to have, again, n products indexed by 1 to n. For each product, we're going to have a revenue RJ, and for each product J, we're going to have a preference weight VJ. So RJ is the revenue product J, VJ is the preference weight of product J. So then, under the nested logit model, the customers are first going to decide whether they're going to make a purchase in our store or not purchase anything. And after they decide they're going to make a purchase in our store, they choose among the products that we offer in the store. Okay, so there's going to be a 2-stage decision-making process, if you will. So then, in the nested logit model, if our product offering decisions is given by this binary vector X, and if the customer has already decided to make a purchase in our store, then the probability that the customer chooses product J is given by the preference weight of product J divided by the preference weight of all available options in our store. Okay, so this is the probability that a customer purchases product J, given that we offer the assortment X, and she already decided to make a purchase in our store. And throughout this portion of the lecture, let me use V of X to denote this sum. This is the total preference weights of the products in our store, given that our assortment decisions is given by this vector X. So that's my shorthand notation for this sum. Good. So this is how the customers are going to choose once they decided that they're going to make a purchase in our store. So then we can write an expression for the expected revenue from a customer that already decided to make a purchase in our store. Namely, if our product offering decisions is given by this vector X, and the customer has already decided to make a purchase in our store, then this is the probability that a customer goes for product J. And if she goes for product J, this is the revenue that we obtain from this customer at overall products. So this is the expected revenue that we obtain from a customer, given that our assortment decisions is given by this vector X, and the customer has already decided to make a purchase in our store. And I'm going to denote that expected revenue by R of X. Again, what is that? That is the expected revenue from a customer, given that our assortment decisions is given by the vector X, and the customer has already decided to make a purchase in our store. And the last component is, how is the customer going to decide whether she's going to come to my store or decide not to purchase anything? In the nested logit model, we're going to have this parameter gamma that is going to take value between 0 and 1. And that gamma is going to amplify or de-amplify the preference weights of the products that I offer in my store. So then under the nested logit model, if the products that we're offering in our store is given by this vector X, then the probability that the customer actually decides to make a purchase in our store is given by, take the total preference weights of the products in our store, raised to the power gamma, divided by the preference weight of no purchase option, plus the preference weights of the products in our store raised to the power gamma. So now I'm putting it all together. If our assortment decisions is given by this vector X, this is the probability that a customer is going to come and make a purchase in our store. Given that the customer comes and makes a purchase in our store, the expected revenue from that customer is given by R of X. So then this is the expected revenue that we obtain from a customer as a function of our product offer decisions. And in my assortment optimization problem, I would like to find a binary vector that maximizes that expected revenue expression. And to tie this objective function to the hammer story that I just told you a couple of minutes ago, this gamma term is kind of useful. If this gamma term is very, very close to 0, that means that if you offer more and more products in our store, this V of X is not going to increase that much. As a result, the marginal benefit from introducing more and more products in our store in terms of attracting the customers into our store is going to get smaller and smaller. So this gamma term captures the fact that captures the story that offering extra hammers that are similar to the hammers that we're already offering may not be useful to bring extra customers to our store. So that is the nice modeling intricacy that the multinomial logit model brings us. So this is the assortment optimization problem that I would like to solve. Okay. When we look at this now, there is an additional source of nonlinearity, this gamma exponent. And again, the trick that we're going to see here is that there's a nice trick that allows us to get rid of this additional source of nonlinearity in our assortment optimization problem. Okay, any questions about the problem that we formulated? Good, so let's try to solve this problem. So without loss of generality, let's index our products so that the first product has the highest revenue, the second product has the second highest revenue, the last product has the lowest revenue. So that's how I index my products, let's say. That's without loss of generality. So we're going to show that the optimal solution to this problem, has a very specific structure, has a very nice structure. So we're going to show that in the optimal solution to this problem, we either only offer the product with the highest revenue, or the product with the highest revenue and the second highest revenue, or the product with the highest revenue, second highest, and the third highest revenue, and so on and so forth. So we're going to show that the optimal solution to this problem that we just formulated includes a certain number of products with the highest revenues. So we call these kinds of solutions we call those kinds of assortments as revenue ordered assortments. So an optimal solution to this problem is going to be a revenue ordered assortment. Why is that result useful? How many revenue ordered assortments are there? Well, offer the product with the highest revenue, offer the 2 products with highest revenues, offer the 3 products with highest revenues. There are only n possible revenue ordered assortments. So if I know that a revenue ordered assortment is optimal for the problem that I'm interested in, I can go back and check the expected revenue of this problem at every single possible revenue ordered assortment and pick the best one that would solve the assortment optimization problem that I would like to solve. Okay, so then for this assortment optimization problem, the main result we're going to show is that we're going to show that an optimal solution to this problem has to be revenue ordered. Then by using the fact that there are only n revenue ordered assortments, we can check each one of them and pick the best one. That will be the optimal solution to this problem. So then the second major result we're going to show today is going to be to show that this assortment optimization problem under the nested logit model admits a revenue ordered optimal solution. So let's do that. Let's do that. Okay. This is the assortment optimization problem that I would like to solve. Find an assortment offering decisions that maximizes expected revenue, and let Z star be the optimal expected revenue in my assortment optimization problem. So we're going to start with the same fractional programming trick that we did for multinomial logit model. So the optimal objective value of this problem is Z star. That means that for any feasible assortment decision, Z star has to be greater than or equal to the objective function evaluated at the feasible assortment decision. And at the optimal assortment decision, this inequality has to be tight. Good. So then let's write this inequality in a slightly different fashion. Take the denominator, throw it to the left-hand side. If you do that, it's going to read Z star plus Z star times V raised to the gamma. Take Z star times V raised to the gamma and throw it to the right-hand side. So then this inequality becomes, we had Z star on the left-hand side, and on the right-hand side, we have V raised to the gamma times R, V raised to the gamma times R, minus Z star V raised to the gamma, minus Z star V raised to the gamma. So these two inequalities are 100% equivalent to each other, which means that for any feasible assortment decision, the optimal expected revenue in my assortment optimization problem has to be greater than or equal to this quantity. And at the optimal assortment decision, this inequality has to be tight, which means that to solve my assortment optimization problem, I can just maximize this expression over all feasible assortments. And if I do that, this inequality has to be tight. So if I maximize this expression over all feasible assortment decisions, this inequality has to be tight. So the optimal objective value of this problem has to be exactly equal to Z star. So now what we obtain from this sequence of 4 panels is that if I solve this problem, if I can solve this problem, if I can solve this maximization problem, that is going to recover an optimal solution to my assortment optimization problem. So if I solve this maximization problem, it's going to recover an optimal solution to my assortment optimization problem. So if I can show that the optimal solution to this problem, is a revenue order assortment, I'm good to go. So we want to show an optimal solution to this problem is revenue order. Okay, that's what we want to show. Good. So we want to show that this problem admits a revenue ordered assortment as the optimal solution. Let's do that. In order to do that, we're going to use this cute little lemma called the linearization lemma. Here's what this linearization lemma says. And we're going to prove this lemma later on, but let me for now tell you what this linearization lemma says. I need to solve this problem to compute my optimal assortment. That is the problem that we have here. That is the problem that we have here. I need to solve this problem to compute my optimal assortment. Let's let X star be the optimal solution to this problem that I would like to solve. Let me define the scalar U star as a convex combination of the optimal expected revenue in my assortment optimization problem and the expected revenue from my store when I offer the optimal assortment. So I define this new scalar. So it turns out that we can show that I can recover my optimal assortment by solving this optimization problem. And if you compare these two optimization problems, what is different? This optimization problem does not have gamma anymore, but instead it's got a more complicated scalar, U star instead of Z star. So that gives me this linearization lemma gives me an alternative way of obtaining an optimal solution to this problem that I would like to solve. So again, what is our linearization lemma saying? Our linearization lemma says the following. Let's say I would like to solve this problem. Let's say X star is the optimal solution to this problem. I would like to solve this problem. Let's say X star is the optimal solution to this problem. I'm going to define this scalar, which is a convex combination of the optimal objective value of my assortment optimization problem and the expected revenue from my store when I offer the optimal assortment. Then it turns out that I can recover an optimal solution to this problem by solving this simpler looking problem. And in this simpler looking problem, I don't have the exponent gamma anymore, but instead I have this other constant U star instead of Z star. So this linearization lemma gives me an alternative way of obtaining an optimal solution to this problem that I would like to solve. I can solve this problem instead of that. And these two problems have the same optimal solutions. Great. So then I wanted to solve this problem to get an optimal assortment. But I told you by the linearization lemma shows that you could actually solve this problem to get the optimal assortment. Those two problems have the same optimal solutions. So then instead of solving this guy, let's solve this guy to get our optimal assortment. Let's solve this guy to get our optimal assortment. This problem has a very nice simple structure. So let's unpack this problem and see what it looks like. Well, let's keep the total preference weights of the products that we're offering in our store. This is the expected revenue from my store when I offer the vector X of products. That is the expected revenue from my store when I offer the vector X of products, and keep U. So this is the same problem. These are the same problems where R of X is written more explicit form. So then let me distribute this V of X over both of these terms. What is V of X? Remember, V of X is sum over J, Vj, Xj. That is the total preference weight of the products that I'm offering. So when I distribute this guy over both of these ones, for the first term, this denominator and this are going to cancel. So I'm going to end up with Rj, Vj, Xj. There is that Rj, Vj, Xj. Rj, Vj, Xj. When I distribute this term over U, what am I going to get? Minus sum over J, U star Vj, Xj. Minus sum over J, U star Vj, Xj. So if I distribute this term over these two, this is the objective function that I would like to get. So that means that if I solve this problem, I'm going to get the optimal solution to the original assortment optimization problem that I'm interested in. Well, let's look at the structure of this optimization problem. Right? Let's look at the structure of this optimization problem. What does it say? Well, for each product that we offer, we're going to get a net contribution of Rj minus U star times Vj. In this problem, for each product that we offer, we're going to get a net contribution of Rj minus U star times Vj. So in an optimal solution, if this contribution for a product J is positive, I'm going to offer that product. If that contribution is negative, I'm not going to offer that product. So then, let's put the revenues of the products on this axis, R1, R2, R3. And the first product has the highest revenue, second product has the second highest revenue, and so on and so forth. U star is going to fall somewhere. I don't know what U star is, because U star requires knowing the optimal objective value of our problem. I don't know where U star is. But whatever U star is, products whose revenues are greater than U star are making positive contribution. They should be offered. The products whose revenues are less than U star are making negative contribution to this problem. They should not be offered. So then the optimal products that I should be offering are all the products whose revenues are greater than U star. There are going to be a certain number of products with the largest revenues. So the optimal solution is going to be a revenue order assortment. Again, since I do not know what U star is, I don't know what revenue order assortment I'm going to go for, but I know that I'm going to go for a revenue order assortment. So we prove that a revenue order assortment is going to be optimal for the problem that we just formulated. Good. Any questions about how we use this linearization lemma trick to prove that revenue order assortments is optimal for our nested logit assortment optimization problem? And I'm going to show you a proof for the linearization lemma in a second, but for the time being, let's just take the linearization lemma as a tool. Okay. So we have about 13 minutes left. So the first thing I'm going to do is I'm going to show you a proof of the linearization lemma. And after that, we can come back and see that this linearization lemma also becomes useful when we're trying to solve cardinality constraint assortment optimization problems under the nested logit model. So let me skip over the cardinality constraints. Let me show you a proof of the linearization lemma, just so that we have a complete picture at the end of this lecture. Here's what the linearization lemma said. That's written in the blue rectangle that's at the top of the page. The linearization lemma said the following. I would like to solve this problem. Let's say X star is the optimal solution to this problem. I want to solve this problem. Let's say X star is the optimal solution to this problem. Define a scalar U that is a convex combination of the optimal expected revenue in my assortment optimization problem and the optimal expected revenue from my store when I offer the optimal assortment. Define a scalar U. So then we're going to show that this optimal assortment X star can also be recovered by solving this optimization problem. X star is also an optimal solution to this optimization problem, where again, these two problems are differing by gamma is not here anymore, but instead we're using a more complicated scalar U star. So if X star is an optimal solution to this problem, then X star we want to show that is also an optimal solution to this second problem. That's the result that we would like to show. Okay. And this uses a somewhat unexpected trick, so I want to show you the proof, which doesn't take too much space. Okay, good. So let's let X star be an optimal solution to this problem. I want to show that X star is also an optimal solution to this problem. So that's what we're trying to do. Great. So X star is optimal solution to this problem, which means that for any feasible assortment decision X, the objective value of this problem evaluated at X star has to be greater than the objective value of the same problem evaluated at some other solution x. So the objective value of this problem evaluated at x star has to be greater than the objective value at any other x that I evaluate. So this is what it means this is what it means for x star to be an optimal solution to this problem. Good. So now I would like to make this term look like the objective function of this problem, the second problem that we're going to be looking at. So in order to do that, let me isolate v of x star over here. So then to make sure that the terms match, let me also divide this guy by v of x star divided raised to the 1 minus gamma. So if you cancel these two things, what do we have? We have v of x star raised to 1 here. We have v of x star. If you cancel them, you're going to end up with just v of x star raised to the gamma. So this and this is taking care of what I have over here. Let me play the same trick over here. I want this guy to look like this final objective function that I want to reach to. So then let me peel out v of x over here and put the remaining portion over on the left-hand side. So I have v of x raised to the 1 minus gamma here, v of x over here. If you cancel this 1 and v of x here, you're left v of x raised to the minus gamma, throw it to the right-hand side. So these two inequalities are perfectly equivalent to each other. I just rearranged the v of x over here, and I just rearranged v of x star over here. Okay. So then for any feasible assortment, this quantity evaluated x star has to be greater or equal to this quantity evaluated at any feasible assortment x. Good. So the only intelligence we're going to use in this proof is the fact that the geometric mean is always dominated by the arithmetic mean. Here's that is. The geometric mean of P and Q is dominated by the arithmetic mean of P and Q. When I'm computing geometric mean, I'm using the exponents of gamma and 1 minus gamma. And when I'm computing the arithmetic mean, I'm using multipliers of gamma and 1 minus gamma. So this is just a general result that we all know from high school that says the geometric mean is always dominated by arithmetic mean. Let me use this identity with p is equal to 1. When p is equal to 1, this goes away. When p is equal to 1, I got a gamma. So I just have this generic identity that says q raised to the 1 minus gamma is upper bounded by gamma plus 1 minus gamma times q. So this is just coming from the geometric mean dominated by the arithmetic mean. So then by using this identity, I can make this term even larger. I can come up with an upper bound on this term. And I'm going to make the right-hand side of this inequality even larger, so this inequality is still going to be satisfied. So this raised to the 1 minus gamma is upper bounded by gamma plus 1 minus gamma times the same term. So gamma plus 1 minus gamma raised to times the same term. I upper bounded this guy by this term, so I made the right-hand side of this inequality larger, so this inequality is still maintained. So we're almost done. We need to do some arrangements over here. We're gonna do some cleanup over here. My pen. So this inequality is going to be satisfied for every feasible assortment. This inequality is satisfied for every feasible assortment. So let's do a cleanup. Take this gamma, distribute over this guy. So you're going to end up with gamma vx star rx star minus z. So this term is taking care of gamma, distribute over this guy. Great. V of x rx minus z, v of x rx minus z. So this term is taking care of whatever is written over here. And now what is left? This one distributed over this one. Well, if I take this one and distribute it over that guy, if I take this term and distribute over this term, Vx stars is going to cancel. You're going to left with 1 minus gamma V of x Rx star minus C. There is that 1 minus gamma V of x Rx star minus C. So this is nothing more than this previous inequality with the terms shuffled around a little bit. But the beautiful thing is now is I got rid of the gamma exponents in all of my V's. So I'm making progress towards the last optimization problem that I would like to get to. Okay, good. So now let's write this expression. Let me get another color if you like. Let's write this expression in a slightly different but equivalent manner. Keep V of x, put this gamma inside. So I have gamma times R of x. These two are going to give me gamma times R of x because there is 1 R of x and minus 1 minus gamma R of x. That's going to give me gamma times R of x. And I have another gamma times z star. And there is my gamma times z star. So this one and this one is exactly equivalent to each other. It's just pushing some terms around. And let me do some cleanup over on the right-hand side. Keep v of x. What else do we have? Minus z, minus 1 minus gamma z. Put them together. That's going to give me a minus gamma times z. And out of x, keep the out of x over here. We kept that guy. And 1 minus gamma out of x. There is 1 minus gamma out of x. So this is this guy. Just we push the terms around a little bit. So these two inequalities are all identical to each other. They are just pushing the terms around. They're just simplifications. They're just minor algebraic manipulations. And lastly, to get to the final result that we're interested in, let's do some cleanup over here. This term is exactly the definition of U star. This term is exactly the definition of U star. A convex combination of the optimal expected revenue in my assortment problem and the optimal expected revenue from my store. So that's a U star, that's a U star. So what we obtained is that at any feasible assortment, this objective function at the optimal assortment, x star, is larger than or equal to the same objective function at any feasible assortment, which means that x star has to be an optimal solution to the problem of maximizing this. Okay, so this linearization lemma comes from just the fact that the geometric mean is dominated by the arithmetic mean and then doing some simplifications. But it is immensely useful because, again, it got rid of this exponent gamma in our in the optimization problem that we would like to solve. Because we could get rid of the exponent gamma in the optimization problem that we would like to solve, we could immediately compare RJs with the U stars and figure out whether each product J should be included in the optimal assortment or not. Good. Let me take another stop here. Any questions, any comments? Okay.
I have a question, Huseyin.
Yeah, sure.
This might be something I had missed earlier. So is there an ordering in terms of size between Z star and this RX star? Like, is one larger than the other?
Yeah, so yes. So Z star is the optimal objective value of this problem. This is less than 1. So R of X is always going to be less than Z star. So that difference is always positive if you are picking at that. Yes.
So you mean Z star is less than R of X star?
Yes. Yes.
Yeah, got it.
Right.
Okay.
So Z star is the optimal objective value of this problem. And this is a number that is less than 1. So Z star is going to be less than R of X star.
So Z star is less, and so then U star is larger than Z star, and so you end up including items whose value is definitely larger than Z star, like the revenue.
Yes, and more. And more.
Yeah, and more. Got it.
Yes. And if you're familiar with the assortment optimization problems under MNL, comparing with Z star gives you the exact comparison. The optimal assortment under MNL, we did not do this in the lecture, right? But we can prove that under multinomial logit model, any product whose revenue is greater than Z star has to be included, and any product whose revenue is less than Z star should not be included. Here, the comparison is with U star, which is a little bit less than Z star.
So for gamma equals to 1, this becomes MNL, right?
Exactly. And for gamma equals 1, then U star becomes Z star. So we indeed compare with Z star.
So but Z star and RX star are not identical for MNL. Is it? Because just looking at the definition, it seems it's still the case that RX star is larger than Z star.
So when we unpack this formula, when gamma is equal to 1, what do we get? Right? So then we get what? Let me just write over here. Yeah.
Sorry. So what is your conclusion?
Okay. No. I didn't do any conclusion. So the first thing is when we unpack this formula, what we get to see is that what we get to see is that we recover the objective function of the MNL assortment optimization problem, and gamma is equal to 1. That is something that we all agree on.
Yeah.
Okay, good. So then the second argument is what? The second argument is when gamma is equal to 1, right? You're saying that R of x is still going to be less than or equal to z star.
Larger.
It's still going to be z of z star is still going to be less than or equal to R of x. Okay, but from a comparison perspective, R of x is completely useless to us. Gamma is equal to 1.
Okay. Now I got it. I missed this part. Yeah. Okay. So by definition, U star is equal to Z star when gamma is 1. That's it. Got it.
So it's completely R of x that is completely irrelevant to us.
Perfect. Thank you.
Great, of course. Okay, so let's go into the wrapping mode. But what I want to say closing this is we can also use the linearization lemma to solve the assortment optimization problem under the nested logit model with a cardinality constraint on the offered assortment. When we did not have a cardinality constraint, we were able to show that the optimal assortment is revenue ordered, and there are only n possible revenue order assortments. You try every single revenue order assortment and pick the best one. That would be the optimal assortment. When we have a cardinality constraint, we can again use the linearization lemma to show that there exist n squared possible assortments such that one of them is going to be the optimal assortment. By checking the expected revenue from n squared possible assortments, we can get to the optimal one. So it enlarges the number of assortments that we need to try from n to n squared, but we can still try, a whole bunch of a small number of assortments and pick the best one to get the optimal assortment when we have a cardinality constraint. So with that, let's not do the cardinality constraint and go into the wrap-up mode. And let me mention a few other useful things. First of all, for those of you who worked with the nested logit model before, you realize that the version of the nested logit model we looked at here has a single nest, but there are versions of the nested logit model with multiple nests. And all of the arguments that we discussed today extend to multiple nests, and we can show that in each nest, it will be optimal to offer a revenue ordered assortment. So you can do assortment optimization with multiple nests in a tractable fashion as well. There are many other types of constraints that we can actually handle for the nested logit model, not only cardinality constraints. There are papers on that. One important class of choice models is the mixture of multinomial logit models. We do not say anything about them today. So in a mixture of multinomial logit models, what are we doing is we have multiple customer types. Each customer type is choosing according to a different multinomial logit model with different parameters. And the choice process that we obtain is occurring as a different customer types coming and hitting me, but I don't know the type of the customer type that's going to come and hit me. Mixing multinomial logit models enriches the choice model that we're working on quite a bit. As I tried to say at the beginning of the lecture, we can actually show that by mixing enough number of multinomial logit models, we can capture any kind of a random utility maximization problem. But solving assortment optimization problems under a mixture of multinomial logit models is quite a bit tricky, and there are no efficient algorithms to solve these kinds of problems. We work with multinomial logit and nested logit model today, and the assortment optimization problem under both of those models were pretty tractable. Then that immediately raises the question of, could it be the case that assortment optimization under any generalized extreme value model is polynomially solvable? The answer to that question is no. There are other generalized extreme value models under which the assortment optimization problem is NP hard. So we cannot say that any generalized extreme value model gives you a tractable assortment optimization problem. And lastly, for the major portion of today, we assume that the prices are fixed. We only make assortment offering decisions, but there are a lot of people that also thought about doing pricing optimization problems under these kinds of different choice models. So let me wrap up with a list of references. This is a super incomplete list of references, so I'll be skipping a lot of my colleagues and friends. So let me start with apologies. So let me just run you through these references really quickly. I love this paper. It's an old paper that's written on a typewriter, so it's got this weird fonts in it, but couldn't be more clear. And this paper is a very good introduction to generalized extreme value models, and it's beautifully written. These three models were I would say the first model. These three papers were the first papers that looked at incorporating choice modeling into revenue management problems. So for us, this is more or less where everything started, if you will. The totally modular constraints that I talked about is coming from this paper that we worked out. These are papers that do assortment optimization under the nested logit model. This is the first paper that did assortment optimization problem under a mixture of multinomial logit models. And several papers followed up on that. These are sort of like the newer papers that did assortment optimization problem under a mixture of multinomial logit models. This is a paper that does pricing under multinomial logit and nested logit models. And this is a paper that does continuous pricing, as we talked about earlier in the lecture. So if you're interested in continuous pricing problems under multinomial logit and nested logit models, this is the paper to look at. And this is, of course, the paper by, this is, of course, the book by Kalyan Taluri and Gerrit Van Ryzen. That's our big reference book. A lot of the results that we talked about came out just after this book was completed. So you can find some of these results in the paper, some of these results in the book, but also some of them are kind of new, not over there. And lastly, this book is a book that Guillermo Gallego and I put together. And when we were writing these papers on nested logit, the results were obviously correct, but our thinking was, not in its clearest when you first face these problems. And if you refer to this book, I think you'll find the clearest presentation of the assortment optimization problems under the nested logit model, and the book is freely available from Springer. So this book shows assortment optimization problem under nested logit model, but slightly different from the papers, because again, by the time we got to the book, our thinking was, I think, was a whole lot clearer. So I'm going to stop here. Maybe we can spend another minute or two to take any other questions if there's anything left. But other than that, we're going to come back on Thursday at the same time. And we're going to look at assortment optimization problems under yet another class of choice models called the Markov chain choice model. That's going to be the topic of Thursday, same time. Any questions, any comments before we stop today?
Sorry, one question. So in this model, the purchase decisions is independent of the prices. Is there any way to mix them together? Because it's intuitive that the prices affect the purchase decisions. We
did, right? We looked at the case where the preference weights of the products are dependent on their prices. So in that case, if I offer this product at $100, its preference weight is going to be something. If I offer this product at $75, its preference weight is going to be something else. So that could be one way of making your purchase decisions dependent on the prices.
Got it. Thank you.
May not be the way that you want it to be, but that's one way to do it. Anybody else? Great. Let's stop here. Hopefully I'll see you on Thursday, same time. Thanks a lot.
Yeah. Thank you so much, Huseyin. Thank you so much for the great session. I think this concludes the session. So I want to thank you, and I want to thank all the participants on behalf of Victor. Victor could not be with us today, so he asked me to conclude the session. And we will meet next Thursday. Anything you would like to add, Huseyin?
No, the video is going to be posted on YouTube on AUB's channel. And the slides are also going to be posted, so the material will be available if you're interested. And I'm happy to chat about this material anytime. So please reach out if you'd like.
Great, thank you all.
Thank you. See you Thursday.